So at this part, I would like to show you the procedure for steel heating simulation according to the Eurocode 1993-1-2. So this simulation is inbuilt inside the IDEA StatiCa, and I would like to show you step by step how it can work if you just put it somewhere to the Matcat Python or the other tool that allowing you some iteration loop. At first, let's describe the procedure. At first, we need to start with some governing equation. I would like to highlight and emphasize that at first, please read out the blog post where all the information are described, uh, and based on that, you will see what we are discussing right now. Because the governing equation is basically for unprotected material, so it means for protected material it looks quite differently because there is like a protection insulation that should be taken into account, and basically decreasing the derivation of the temperature over the time. There will be different equation. So let's go through the equation. This equation, what you can find inside. So you can find inside some correction factor for shadowing effects. IDEA StatiCa consider factor 1 that is conservative, is hard-coded, and cannot be basically changed. So another is the section factor ratio. Basically, as you can see, the unit is 1 divided by meter. So in the denominator there is like a meter, and it's basically heated surface area divided by steel volume. As you can see that this equation, or this is like a constant, but this constant will be changed for every single plate. Another variable is net heat flux that is composed from the convection and radiation, because we are just talking about the flames, about the fire. So there is just the something what is in the air and just floating in the air, and it's coming from the radiation, and some part of the heat that is coming from the convection. So emissivity from the radiation and floating from the convection. Um, Another factor is density of the steel. So steel is playing a big role in the conducting of the heat. So as you can see, it's in the denominator. So if the density is higher, so this derivation will reach lower value, and you will reach at the end the lower temperature. Also the specific heat, as you can see it, like describing you how many heat is able to go through the 1 kilogram of the material, and how the temperature will change about the 1 Kelvin. So it's basically temperature dependent characteristics. Okay, so we just described the equation. So let's move to the heat transfer mechanism. So at first, we need to calculate the total heat flux, and the total heat flux, as I mentioned before, is composed from the convection and the radiation. All the equations are very well described in the Eurocode 1993-1-2. What is very important to specify, what is already implemented by default and assigned by default in the IDEA StatiCa, is basically the convection heat transfer coefficient that is set as 25 watt per meter square Kelvin. And for radiation, as you can see, what is outlined in this equation is like a configuration factor that is reaching 1. Surface emissivity, that is also the variable that can be assigned and inputted into the setup of the IDEA StatiCa, but by default I think there is like a 0.7 as here. Also the Stefan Boltzmann constants, that is just a constant. You need to just take it over and just put it to the equation, and absolute temperature in the Kelvin. So those are the variables that are implemented inside this equation. So what about the gas temperature? The gas temperature is dependent on the fire curve that you select from the library of the existing fire curves. We support four curves for yeah, fire curves in general. So I've just selected for the simulation the external fire curve, and based on that, you can see what is the evolving of the curve over the time. So that's this equation. As you can see, it's in the exponential form, so we can expect like not linear progression, but the exponential progression. And yeah, here is just the description about the specific heat of the steel. So as been mentioned, the specific heat is dependent on the temperature because we need to take into account the, changing of the state from the solid to the basically to the fluid, and there is just the melting point that is highlighted in the code in the graph. So and I would like to get the output, and the output will gives me the final temperature, but also the distribution, the temperature over the time with comparison of the gas temperature. So I will get the history output of the temperature, and also the animation that will be providing some insight how the temperature is changing on the plate. So at first, let's go to settings of the variables. So, or the constant is density of the steel. Here you can see this is just a function that is defining me the temperature or the specific heat. So you can the specific heat. Here is the definition or the function that is returning me temperature, the temperature in the relevant time. And let's discuss the inputs. As I mentioned before, at first it's very important to read out the article to know why I just assigned this section factor 146.36. As you can see, this is the convection heat transfer factor 25, emissivity, Boltzmann constants, and coefficient for shadowing. Actually, delta t is the increment because we need to, this is just the iterative approach, so we need to assign the increment. Of course, if you reduce this number, you are just more closely to the precise solution. So and if you increase this delta t, so when the number is starting to be bigger and bigger, so the error is also bigger and bigger. Yeah, so just I think the setup in the IDEA StatiCa and the recommended step or increment is 5 seconds. So as I mentioned, it's written in the article. I just selected the resistance R15. So it means the structure has to sustain the load about at least 15 minutes. So as you can see, that's been recalculated to the seconds. So right now, let me just jump into the loop and show you how it works. So I will just step into the debug mode. As you can see, all the variables or all the arrays has been displayed, and let's step into the function. So at first, I need to just take the time from this array. So the first step or the time in the array is 5 seconds. So based on that, I will just recalculate the seconds into the minutes. So as you can see, this is the value of the minutes, and theta g is about basically the temperature of the that is coming from the function of the gas. So for external fire curve. Yeah, so if I calculate it, it's 88 degree and steel temperature. So this is just the ambient temperature around the steel. So we consider like a 20 degree by the default. That is also the value implemented inside the IDEA Statica and inbuilt and cannot be changed by the user. Um, a specific heat. So right now we are just stepping into the function. So I just look into the function and see if my data, like a temperature, is lower than some condition, and based on that, I will just reuse the equation. So as you can see, the temperature is lower than 600 degrees, and we can just step into the equation 439, and we need to use the absolute values in the Kelvin. So as you can see, I just count it together, and I'm approaching to the calculation of the total or sum of the basically convection, or at first I need to calculate the convection, radiation, and I need to make a sum of that. If I will do it, I can I'm at the end of the loop and stepping into the governing equation. So right now is calculated the derivation phi according to the time. So what I will get is 0.088. This is my first increment. Right now I need to use the ambient temperature plus the increment times the delta t, and the delta t is my increment of the time. So and if I have it, I need to assign this temperature as a steel temperature. So this is my first initial state after this increment, and I can do it in the loop because I need to looping all the increments and use all the increments in the arrays of the time. So if I will do it, as you can see, I'm just going to the second iteration and running the procedure again. So the temperature has been increased to 21. Yeah, and if I will do the third iteration, so there is just the 22. As you can see, there is just the increasing of the temperature over the time. It's starting to like a slowly, but there is like an exponential trend. So you um, you will see that the temperature will be changing non-linearly or based on the exponential function that you're using for a gas. Okay, so I will just stop it here and go to the displaying of uh, of the temperature on the plate or on the stiffener. So if I will just run the code, you will see that what I will receive. Yeah, okay, it will take some time. So that will appear. Okay. Okay, just stop it. Try it again. And we'll see. Yeah, here is just the last part is dedicating to the plotting of all of the informations. So I just use the animation because the animation gives me better overview and the perspective how it works. So as you can see, this is the gas temperature, and the red curve that is changing over the time is the temperature on the plate. So basically, as you can see, the temperature is uniform across the whole length of the or whole stiffener because there is just the section ratio is valid just for whole um, plate or member. Yeah, so this is the reason why you can see the temperature is the same or uniform across the whole um, stiffener. Otherwise, the temperature is changing from the one side to the others in the more like a transient way if we are talking about the real behavior of the plate. So I do believe that it helped you to understand what procedure is behind, and yeah, that's it. Thank you.